Okay, apologize for running a little bit behind. Had a lot of questions in my brief calc class, which might be the thing going forward here. We're getting close to the first exam, aren't we? Something like today's the last day of new material. Um, so we're going to take a look at 2.6. We're going to finish up 2.52. We have a little bit left to do, so we'll do that. We'll look at 2.6, which is going to be applying what's today? Thursday. What we learned on Tuesday. This week seems weird. I feel like I'm starting over again because of the holiday, but we're actually almost done, right? How many of you don't have classes on Friday? Awesome, me too. I just love having one open day where I can get my work done. Okay, so today we'll finish up with the content part. Tuesday will be review. So to get you in the mindset, so maybe this weekend as you finish up 2.6 and continue working on the homework, the homework should all be extended up, and there's like a secondary due date. It shouldn't be subtracting any points, although sometimes I go in there and it shows somehow it like takes 15% if you do it after the first due date. I'll figure out if that does happen. I'll get you posted up there. But the main thing is to get through the homework. My goal with the homework is it's a formative. If you can at least work through all the problems, do well on those will help prepare you for the test. So those should continue to update as we get closer to the exam. For the review, let me come back here. I think we do have, what do we have here? Each class. So there is a exam one review, and there is a solution guide for it. This exam one is just a place to keep track of the it's a place in the grade book. Okay, so anyway, there is this practice test. It's a review. So again, if you can work through that this weekend, it's the basis of what I'll use for our review session, which will be pretty much open. It'll be an opportunity to ask any questions. I'm doing the same thing in my brief calc class, but what I will do is I'll trade off and I'll maybe look at some of the more difficult ones in here, and I'll make some solution videos as well. So again, if you're having problems, check up on that. I'll put announcements. Yes. Yeah. So this is the one provided by and it's provided by the coordinator. It's also on for each class we have sort of a little website. These reviews are provided there by the department, so those are good. Our exam will be paper pencil, right? So it's not going to be through Pearson, but Pearson will bring you questions that will be good to practice with. I will look it up. I haven't gotten the actual exam yet, but I was told it's around 20-ish questions, 12, 13, 14, something like that, multiple choice. So again, you've got a question, you've got all the answers, you just need to select the right answer. It's helpful if you do show your work on those, and then there's a few questions, 6 for whatever, the rest of them that are open answer. So there's a question, you're supposed to provide your work and give me an answer. Let me just tell you, don't worry so much about what kind of work do I have to provide. You just need to provide anything that you're thinking, put it down. If you give me a correct answer and you have work that supports it, I'm happy. I'm not going to get too detail in it. If you don't get the correct answer, then I've got to go back to the work to see where it went off. And so the more you provide, the more partial credit I can give. But if you give me a correct answer in some sort of work that's at least somewhat on track, it can't be, then we're good. Okay. But I know sometimes it's this, some of you, maybe do a lot of the work in your head and you don't know necessarily how to get it on the paper. So if you're doing the right processes, we'll make sure that that's all going to work out. All right. Any questions before we get into today? Okay. So I'm going to go back to 2.5. I think, yeah, this is where we sort of left off. I'll pull up the lecture slide deck. There's one topic that we didn't get to cover. And so I'm going to kind of do a little bit of review. So this was looking for zeros of polynomials. So the one thing we did do is that there's we went through this rational zero theorem where P came from the last term, the constant term. It was all the factors of that, and then the divisor, the denominator came from whatever the coefficient of the leading term was. So when it's 1, that was kind of nice. But this would tell us all possible zeros. Those might not be zeros, but it did give us some candidates to check that one of those might be a zero, right? So we went and did a couple examples. So like on this one, we've got a 4 at the front, a -3 at the back, and we looked at it could be combinations of pluses or minus. So plus or minus 3 at the top, plus or minus 4 at the bottom, and again, all the potential multiples of these numbers. So for in the top, we could have a 1, a plus or minus 1, or a plus or minus 3, because 1 times 3 is 3. 4 could be plus or minus 1, plus or minus 2, because 2 times 2 is 4, and it could be plus or minus 4, because 1 times 4 is 4. So we'd look at all these combinations, right? So that was that theorem. And again, you could look back at it. There's some examples in here. We did all of this. And then it would give us potential zeros. And the way we would find those zeros is we'd go back to what we did in 2.4, which is synthetic division. And if we don't end up with a 0 for a remainder, it doesn't divide in evenly, so that didn't work. So we did these where, this doesn't work, this doesn't equal to 0, that didn't work. So nope, these are not, -2 and -1 don't work. But if we go to this one, if we put in 2 and we do the synthetic division, we end up with a remainder of 0, so that divides in evenly. That means 2 is a 0, right? Okay, so that was good. And then we also talked about, so what we ended up with is it factors, and we were left over with a quadratic factor, and so then we could use a quadratic formula to find the rest of it. Because once we get a function down to quadratic, we have a method that always works. Quadratic formula will always give us zeros. There is no things for cubics or fourths or fifth powers, so that's why we use this to get it down to a quadratic, and then we could get them all. If we can't get it down to a quadratic, we're stuck. We can't get them. And that's the thing, is there's a lot of functions out there where we can't use these methods. And that's where there's a whole field of mathematics that has really developed over the last 20 years. It's called numerical analysis, using computers and graphs and stuff to do all this stuff. And those can always find solutions, but they're, needs a computer most of the time. Okay? So we could find all the factors, all the zeros of a function. So we did some of these. We talked about if there is a imaginary or a complex zero, how many are there always? You can't get one, right? It's always got to have a partner. It has its conjugate. So imaginary roots, imaginary zeros come in pairs. There could be more than 2, but there's either 2, there's 4, there's 6. They always come in pairs. And it's because they come from the quadratic formula, so you get that plus or minus thing. So we did those. It's a long day. And then I'm trying to get to, we got to this fundamental theorem of algebra saying that basically everyone can be written, any polynomial can be written down as a series of linear factors. Again, it might be more difficult, than there could be some fractions in there, but we talked about this method, and this is where we left off, is getting to Descartes' rule. Descartes' rule, Descartes is a French name, so my French accent is terrible, although that is part of my culture. My mother was raised by her grandmother, so she cannot still understand, or she was able to understand French most of her life, because until she was 5, that was the only language she was hearing. Of course, it was a a version of French that they spoke in North Dakota. Anyway, Descartes. So here's the rule: is with Descartes' rule, and again, this was developed by looking at patterns. This is sort of what worked. And Descartes recognized that if you look at how a sign changes between, so this is a positive sign, and if it changes, it would be the next one would be negative. If it doesn't, then that's not a change. So he just looked for how often does a sign change. Okay, so that's what the rule is. So the number of positive real numbers, positive real zeros, positive zeros, so x would be a positive number, be a 0, is the same as the number of sign changes. So as you go and you start at the beginning, if it's positive and the next one's negative, that's one sign change, right? If it's positive and positive, that's not a sign change. If it's negative and negative, that's not a sign change. So he's looking for, go from positive to negative or negative to positive, count how many times that happens. If it happened 5 times, it means there's potentially 5 positive zeros. 5x values. So that's what we do. And it will either be that number, right? So the same as the number of sign changes. If there's 5 sign changes, it means there's 5. There could be 5, or it would be less than that. Can't be more than 5, but by a positive even integer. So if there's not 5, there could be 4 or 2, but there couldn't be 3 because it has to be even. So it's either 5 or 4 or 2 or none, because 1's not an even number either, right? So in that example. So for this one, we just count the sign changes, and that either tells us how many positive zeros there are, or there's less than that, but they're all even numbers, because then they're kind of paired up. Let's see. If f of x, if the function has only one variation in sign, then f has exactly one positive real number. So that's the one that, yeah, only one sign change. So we'll look at some examples. His rule also tells us about negative sign changes, or sorry, negative real zeros. And that is the same as the number of sign changes in, notice how it's changed. You have to check the function at negative x. So we have to do a little bit of algebra. Again, if we've got an odd exponent, right, an odd number of negatives will change the sign. If it's a positive, like x squared, it doesn't matter. Negative x squared is positive x. So we'll do a couple examples of that. But then you still count the sign changes with this. And again, it's sort of the same type of rule. It's either the same number. So if there was 5 of those sign changes when you checked it this way, there would be 5 negative zeros. So x would be -2, -3, whatever those. Or again, it's a positive even integer. So if it's not 5, then it could be 4 or 2, but again, not 3 or 1. So you either get 5. So what we're going to do, we'll count the sign changes, and this just tells us. It doesn't tell us what they are. It just tells us how many we would have. Okay, so that's why it's not as much. So here's an example. So we'll use Descartes' rule of signs. We count the sign changes. So we start off positive, and then we go negative. So there is one sign change, right? So that's 1. Negative to positive, there's another sign change. That's another 1. Positive to negative, wow, we're getting lots. There's another sign change, and then negative to positive, there's another sign change. We add these together. How many sign changes were there? There were 4. What does that mean? Potentially we could have 4 positive zeros. So x could be a 1, 2, 3, 4, 5, whatever. So there's 4 potential positive zeros. If there's not 4, however, how many more could there be? Be less than 4? Just 2. Couldn't be 3 because 3 is odd, 1 is odd. So it's 4 or 2 positive zeros. Does that make sense? Just count how many times it changes. To find out the negative, which so that was the positive. So positive is either 4 or 2, or 0. It could be 0, right? I suppose 0 is a positive number. For the negative ones, what we have to do is we have to then figure out what's this function going to be at negative x, right? So since the first term is an even integer, if you plug in negative x there, put it to the fourth power, it's going to stay positive, right? So I'm going to emphasize that this becomes positive x to the fourth. If I put a negative x into a odd exponent, which is this one to the third, now this sign is going to change because it becomes, right, three negatives. A negative times a negative. This is now going to be positive 14x to the third. So this one is a square, so that sign won't change. 71x squared. This is to the first power, which is an odd power, so the sign will change. So the negative becomes positive. And then 120 doesn't have an x, so it stays positive. So so now we're ready to count sign changes, right? So this is how we have to do this for the negative. And what we see is there are no sign changes. Positive, no, that didn't change sign. That didn't change sign. That didn't change sign. That didn't change sign. So there are 0 negative zeros. It's kind of, there are none. Does that make sense? Okay, yes.
I might have missed something, but so the first term doesn't change, you don't change the sign first.
Well, in this case we don't, because it's x to the fourth. It's an even power. So if you put in so thinking of,
oh, that makes sense.
yeah.
Okay,
So we did negative x to the fourth. So I actually did something, but that's going to give me positive x to the fourth, right? Because there's negative, 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 negative. So that becomes a positive x to the fourth. Had the first term been x to the fifth, right? I would have done this, and it would have changed the sign. So it's just, so basically for the second part, you just look, if it's even, just leave it as it is. If the exponent's odd, change the sign. And then count the sign changes, and that's going to tell you how many negative potentially there are. And what you'll see, if there was no positive, then there'll probably be a lot of negatives, because that's, but, and again, it doesn't tell us what they are. We'd have to go back to the other one to actually find them. It just tells us how many we could potentially find. And so what it's doing is, remember, what is a 0? Well, that's where it crosses the x-axis. And so it tells us that there's potentially that this graph could cross it 4 times. It's 1, 2, 3, 4 on the positive side, but it's never going to cross it on the negative side. So maybe it just goes like that. So that's what that's telling us, is we could kind of get a vision of what it might look like. But we don't know if it looks like that or if it goes the other way or something. But we're getting some things here. And again, remember these things, Descartes, I think he lived like in the 1700s. So these are old techniques for people who had to work without computers or graphing stuff. So they had to have these techniques. We would probably just graph it and see what we get, right? We've got tools that will help us with this, but part of what we're learning is these older techniques. And the cool part is sometimes these do help us with new methods we might be developing. And again, if you're going into engineering, you may find a pioneering thing. Well, this old rule in this system, we can't really graph it yet, or maybe we're in 3 or 4 dimensions, but it translates here, and maybe it's helpful. So that's why we give you all the stuff, built you up there. And this is, I just had the PowerPoint goes through it, so they show you, if you didn't like my chicken scratchings, here they'll walk you through it. And there's 4 sign variations, just like we did. So there's 4, 2, or 0. Okay, and then they do the same thing. Yes. Right. So if I get back to so it could look like this, or it could look something like it goes like this, and then maybe it doesn't cross the x-axis, but it will have those 2 imaginary roots, right, up there. But so it could look like that. We don't know, but yeah, that's what this is saying, is it could have 4, or it could have 2, or it could have none, because then it doesn't cross at all. But actually, and it tells us because of those signs, it's not going to have 1. And it kind of, in the theory, is looking at how things would factor and those kind of things. Why does it work? I really don't know. And I don't know, I haven't really taken the time to look through a proof of it, but obviously there's something like that. Probably he recognized patterns, and that's how he did it. I just don't. It's sort of a tool in the toolbox. It does work. And then for the odd ones, they plug it in. And again, they actually went through the process of plugging in. I'm just going, well, if it's even, it's going to stay the same. If it's an odd sign, it changes. You could kind of see that here. So there are no variations in sign. So there are no negative roots, at least no negative real roots. Again, there could be some imaginary roots over there in the negative side, but no real ones. And we're done. That's it. So that's all we missed. I maybe expanded it a little bit further than, probably would have done it in 10 minutes. I did it in about 20, but we also got a little bit of a review, right? So that's the last part of 2.5. So now we're going to incorporate these techniques that we've been using, this division. So we had long division, we had synthetic division, we had this rational zero thing that helped us identify some potential zeros. If we could find them, then we could reduce it. And then now we're going to do, what are we doing? We are doing rational functions and their graphs. So those were some of the techniques to try to build graphs from the old times. Again, we can always graph things with our calculator, so that's what we'll move into. So rational functions. And you'll notice I kind of come back to this is from my other class, because we do this in my other class. In the MAT170, it's not the STEM based. We talk about this, but we don't use the first two techniques to do it. So we've got a few extra tools that we could potentially use, but now we're getting into talking specifically rational functions. So what is a rational function? It's two polynomial functions with a numerator and a denominator. So maybe we oftentimes will use p of x and q of x, f of x, g of x, but it's a fraction with two functions on it. It's something like x squared plus 2x minus 4 over x. Okay. Sometimes it can be reduced, but anyway, so these are the types of functions we're going to be dealing with. There's something in the denominator that has an x. Okay, there we go. So our rational function. And so sometimes we're going to just talk about only the top function itself, because that's actually, it gives us certain things like zeros. Those will come from the numerator. Asymptotes, those are the places where the function becomes undefined, and it's because we're dividing by zero. So we only look at the denominator to find those. And then sometimes we look at the ratio of the two, but it's kind of like the function is both of them together being divided, right? So and that's why we did some division. Sometimes we can simplify and stuff like that. So here we go. We get a vertical asymptote, and that's where x approaches as x gets closer to some number. And what that's happening is that'll happen whenever q of a equals 0. So when we plug in a, the denominator becomes 0. That's going to give us, generally it'll give us a vertical asymptote. Sometimes, depending upon what's on the top, if that factor canceled out, it might give us a hole in the graph. So sometimes, but it always gives us a part that's undefined. Okay. Oftentimes it's where we'll see vertical asymptotes. So what that looks like is that when we get to a, the function goes off to infinity on one side and maybe on the other, like that. So it kind of, what happens, it's avoiding a. X equals a, we've got this vertical line there, that's an asymptote. Is that okay with that? Maybe some of this should be review, but It just depends. So we get horizontal asymptotes, and that's y equals b. And again, what that's going to be is horizontal would be like up here. And that will happen, what we're going to see, there's three cases for that. That happens, we have to look actually at the top and the bottom. It's the ratio between the two. And when we're talking an asymptote, a horizontal asymptote, we're looking at what happens when x goes way outside, when it's going towards negative infinity or positive infinity. So that's where we get our horizontal asymptotes. And again, there's three different cases. And we're going to look at both the top and the bottom, what their ratio is. Vertical asymptotes, we only look at the bottom denominator. Whenever that's 0, that's going to give it to us. So that's the things. So let's take a look at a couple examples. So here we've got this. If we're going to find the vertical asymptotes, again, what's causing a vertical asymptote? Division by 0. So the way we find them, we don't care what's in the top. We really just don't care at all. We only care what's in the bottom. We take that off, and we set it equal to 0, because when that happens, that's where we're going to get an asymptote, a vertical asymptote, right? So how do I solve this for x? We could subtract 3. You could also add x, and you might get done faster, but it doesn't matter. So typically we're told, subtract 3. So we get negative x equals negative 3. But we want positive x. What is it equal to? Multiply both sides by negative 1 or divide by negative 1, however you want to think of it. And we get that we're going to get a vertical asymptote when x equals positive 3. Is there another one? No, that's the only solution, right? So when x is equal to positive 3, we're going to get a vertical asymptote. And as you see, I've got my Desmos here, so we'll actually graph this. And I'll put, let's see, what was it? It's x squared divided by x minus 3. And I like using Desmos because, okay, you see it goes down here, but, oh, what's happening over there? Sometimes we have to zoom out a bit, which, again, I might just go like this. There we go. There's the rest of the graph. What's happening? This, the TI-84 won't do this, but Desmos does. I can actually graph. I can put in x equals positive 3, and there's my vertical asymptote. It's not part of the graph. It's where the graph doesn't exist, so I'll make it a dotted line, or maybe a dashed line, whatever. But that's what it is. So part of this is we want to be able to analytically get there, but if you graph it, you'll see it, and you'll say, okay, that's what it's looking like. So as it gets close to 3, what's happening is it shoots off either way. Yes? We have a problem with the problem I have with that is the department says no, because you need a device that has internet access, right? There is a version of Desmos that will allow you to sort of lock it out, but with this, it's hard to. So the simple answer is no, because the department. I would like to. I allow it in my online course because when they're taking it online, we use a lockdown browser, and I can block out everything else except for Desmos, and I'm perfectly. So I have no problems with Desmos. The problem the department has is if we open up that. In this class, we don't have lockdown browsers, so they're afraid you go to something else. So I think it's a good thing to learn from, but then also use your graphing calculator. Learn to use the handheld, because those you can use. Okay, so I kind of do both. These are great for teaching and learning, but then learn how to, when you've got your graphing calculator, what it's going to look like, because it's a smaller window and stuff, and that's what we can have you use. I'm with you. I'm pushing for the day when we can actually use these techniques, because these are great tools. Yes, and they build understanding. So But I'll use it in the review and stuff, and again, understanding the concepts, and then when you learning how the tool that they let us use. Um, but okay, that's all we needed to do there, right? So we're back here. Oops. Here's another one. So vertical asymptotes for this second one. Let's change colors here. Let's go with green. All we need to do is look at the denominator, right? So x squared minus 9 equals 0. How do I go about solving that? What's that? I could. Okay, that'll work. So there's two ways to do this. So then I get x squared equals 9. Take the square root of both sides. The thing I don't like about doing this is I always forget when you take a square root that you actually get a plus and a minus. I forget that part. So we actually get two answers. We get x equals positive 3 and x equals negative 3. The other way we could go about is we could factor that x squared minus 9 factors into x plus 3 and x minus 3. I usually go this route because then I know, okay, plus and I don't forget one of them. Here I go with the positive 3, I forget about the negative 3, and I mess up. But whichever way you want to do it. So yeah, you could solve it over and get the square root. You could do this, and either way you get x equals negative 3 here. And then you solve, you add 3 to both sides, you get x equals positive 3. So those are the two places. And again, what are those? If we were to look at the graph, because that's what we're trying to do here, at negative 3, we will get an asymptote. At positive 3, we will get an asymptote, a vertical asymptote. And so what's happening, I don't know, maybe it's going here, maybe it goes there, maybe it goes there. So, but it's some sort of combination. Part of it we'll look at, there's ways to tell that, but that we got to look a little bit deeper. But again, we'll go back to Desmos and we'll graph this. So we had f of x equals x minus 3 divided by x squared minus 9. Oops. I'm glad I did that. Let's see, where are we? Does anyone... Oops, not that one. So I look at the graph, but Little Crow said there's supposed to be an asymptote here at 3, and I don't see one. Does anyone know why there's no asymptote here at negative 3? Or at positive 3? There is one at negative 3. I can see that. Good. So I can graph x equals negative 3, and I see an asymptote there. Notice what's in the numerator. What happens here at x equals positive 3? Whoops. See that? When x equals 3, if I can stop at the right place. What's there? Nothing. A hole. A hole is there. The reason it's a hole is because, and actually I can write right here. Notice if you do the factoring, that's the other reason I go with the factoring. We've got x minus 3, and in the denominator we have x plus 3 and x minus 3. Algebraically, we would cancel these out, and that's why it's not an asymptote, it's a hole in the graph. So there's really a little hole right here. But it doesn't, you're looking at, it's such a tiny hole, it doesn't even look like a hole unless even when you zoom in, but there's a hole there. Okay, so that's part of the reason is if you go to graph, because if it's asking for vertical asymptotes, right, there really is not one there at x equals 3. Even though I'll just look at the denominator, I got those, but because of what was in the numerator, because there was an x minus 3, that's going to cancel. It's not actually an asymptote. it's a hole. It's still a place that's undefined, because when you plug it in originally, it does. And that's always hard to understand. You go, well, algebraically, I could just cancel these out, right? So that it should be fine. But because the original function includes there, if you put a 0 in here, you get division by 0. Or sorry, if you put a positive 3, you still get a 0. Okay, so you get a hole there. So the correct answer, back over here, is going to be, yes, there is a vertical asymptote. Let's go back. There is a vertical asymptote here. This is not. There is a hole in the graph at x equals positive 3. Okay. So sometimes we think we can get away with just looking at the denominator, but we always got to bring in that numerator sometimes. Okay. And doing the graph. Again, we may not have Desmos, but have a graphing calculator, TI-84, NumWorks, Casio, whatever, but have a graphing calculator. That's why, because you can always graph them. And that's going to help you. You'll know where the answers is. And sometimes when you know the answers, you can work backwards. So it's a good tool to have. Questions on that one? Okay. Yes. It would show up as undefined. And let me show you that. So most of you have a TI-84, right? 83. Let's go ahead and hopefully it just lets me open it up. And I'll tell you, there's two ways to kind of look at it. We'll look at the graph, and the hole will show up usually most clearly on the table. So if I go to the table and I look up x on the table when x is 3, I'll see undefined. It may be hard to trace over it. Okay, here we go. So what was my function? Let's get this clear. What was it? It was x. So if I go to alpha f1, it gives me numerator over denominator. So it gives me a template. This is so since we're doing rational functions, if you've got a TI-84, if you take that step first, it's a lot easier, so you don't have to worry about parentheses. And now I can do x minus 3. And then I can go down to the denominator, and I can do x squared minus 9. I'm going to go for a zoom standard, number 6. That gives a sort of the starting window. I think is a good place to go. And then I see this, and I don't see it here. I could go to trace. Let me trace along here. Thing is it may be hard to get exactly onto 3. Let's see if it won't let me get directly onto 3. However, there is a way. If you go second calc, you can go to value, and when you do that, you can plug in 3, and it just shows nothing there for y. So that's, which means it's undefined. If I go to the table, second table, and I get an error at -3, and I also get an error at 3. And again, I've got to interpret that's a division by 0. That's what that error is coming. And but see, it doesn't really tell me, but I have to, looking at the graph, I see, okay, -3 gives me a vertical asymptote, +3 must be giving me a hole. So you can, but you have to know what you're looking for. Okay, does that help? All right, and we're almost done, actually, because there's only those 3 things that we have to look at. I think that's all we do. And again, we'll come back. Anything that we need to pick up on, we will pick up on Tuesday. So again, if you can get as much of the homework done as you can, or at least work through it. If you can't get it done, at least know where you have questions. We can look at homework questions. We can look at the review questions. I will steer you if because hopefully by then I've seen the test. So if you might have a pressing question, if I know it's not on the test, I will, in my way, say that's not so important right now. It's not that I'm trying to put you off, it's that I'm trying to indicate that. So I want to steer you towards the things that are going to be on that test. And I'm going to make sure that we get there. Without necessarily saying, hey, this one's on the test. I will say, this is very important. So there's some code words that we use. If I say if it's important, it's the same thing as saying it's on the test. But I don't know who I'm fooling with that, but I know if you got since I record these, it goes out, so I know everything I do is getting recorded, and I'm not trying to scam anybody, I'm not trying to cheat anybody, but I just want you all prepared for the types of things that you're going to fix. So horizontal asymptotes, there are 3 different things that can happen. The thing is when we have a function, so we have, oops, let's come back here. Oh, case 1, okay. Can't remember which so we've got, say we've got x to the 5th plus x to the 3rd or something, and then this is like x to the 2x to the 5th plus x squared. When we're looking for horizontal asymptotes, that's when x is getting really, really big. And again, this is where you sort of start your calculus class at. We're looking as x gets really big, what's going to happen? Well, here's the 3 cases. Is we could get something where the bottom gets really big, sort of goes to infinity, but the top doesn't. It's, it's a little bit less. So we get something like this. So if you take 1 divided by infinity, or 1 divided by a big number, what are you going to get close to? 0, right? The other thing that could happen is the numerator could become much bigger than the denominator. So that's the same thing as going to infinity over 1. And if you have infinity in the top divided by 1, what do you end up with? Infinity. Because you divide by 1, 1 doesn't do anything. So that's another case. The other case is if we get 2 that are relatively close to each other, it's like infinity to infinity. And if you take infinity and divide it by infinity, you'd get something like 1. And now, theoretically, that's all, but that's basically that's where the 3 cases are coming. So, okay, so case 1, 2, 3. So I can make up whatever I want for case 1. So I'll make case 1 this time. What if we had, let's take this one, x to the 5th plus x to the 3rd over 2x to the 5th plus x squared. Now what we're looking at is as x gets really big, the only things that's going to matter is that x to the 5th, because that's so much bigger than even x to the 4th. Take a big number, x to the 5th is so much bigger as x gets bigger and bigger, that all we have to look at for these is the largest degree. And that's the key to analyzing all these 3 cases. So we ignore the small stuff. So like, have you seen the book? There's one that's called Don't Sweat the Small Stuff. This is the math of don't sweat the small stuff. Everything is small in comparison to the largest degree. So we get to just say, okay, as we're getting really, really big, either positive or negative infinity, we just have to treat this thing as if it were x to the 5th over 2x to the 5th. And now using algebra, can we reduce this further? Yes. So x to the 5th divided by x to the 5th, like infinity over infinity, that's sort of like 1. And so this is going to become 1/2. So it's basically whatever those coefficients are, right? This is 1, so it's 1 over 2. Whatever those coefficients are, if they're the same degree, both to the 5th power, both to the 27th power, whatever, those are all going to cancel, so just the numbers are left. That's our horizontal asymptote. So this is y equals 1/2. So what that looks like on a graph is that when so if this is y equals 1, we would see in the long run that the graph is going towards 1/2. The y values are going towards 1/2. It's not, there could be some crazy stuff going on in here, but eventually it will go to 1/2, either that way or maybe this way. Okay, so it doesn't say what's happening in the short term, but this is a long run behavior type thing. Okay, so that's case one. Both degrees are the same. Everything cancels out except for those coefficients, and that's y goes towards that value. So that's one answer. Is that okay? Make sense? Sort of? Okay. Case two. So they're not the same. And this is where we get case two and case three. So one case is the top is bigger than the bottom, the other is the bottom bigger than the top. It doesn't really matter which one we call case two. How about if we do x to the fifth? How about 2x to the fifth and 3x to the fourth plus stuff? And again, you remember whatever's there, it doesn't matter. So I can make it as complicated as I want, but it doesn't matter because it's all going to be small stuff in comparison to the biggest degree. So I ignore all that stuff, but I take this and I take this, and that's how I do my analysis. 2x to the fifth over 3x to the fourth. I now apply algebra and reduce or cancel out as I can. So these x to the fourth cancels with 4 of these, so that leaves an x to the first. So this is going to behave like 2x over 3. And as x gets really big, what's going to happen? The top is going to infinity. We take infinity divided by 3. It doesn't really matter. This thing is going to shoot off to infinity. There is no horizontal asymptote. Okay, so it's diverting to infinity. No horizontal asymptote, HA. We'll do that. Okay, so when the top is bigger than the bottom, it goes off to infinity. Could go off to negative infinity, depending upon the direction. So it's going either positive or negative infinity. No horizontal asymptote. Case 3 is when the bottom. Question. Right, you're sort of subtracting the exponents. Yes, division. So 5 minus 4 is to the 1 power. Case 3, we could just reverse it. So 7x to the third over 5x to the 13th plus other stuff, plus other smaller stuff, right? Again, we can make up anything we want, but all we need to look at is the largest degrees. And so this is going to behave like 7x to the third over 5x to the 13th. 5 and 7 are still there. These 3 x's cancel out with 3 of them down here, so we're left with x to the 10th. All right, so this is like 7 over 5x to the 10th. And again, as x goes to infinity, I've got infinity to the 10th power. It's really big, but the denominator, so I'm dividing by big numbers. What do I end up getting? Something like this. I'm dividing by very large numbers. This, when the bottom is bigger, this will go to 0. So y equals 0. And where is y equals 0 on a graph? It's the x-axis. It's not just the origin's part of it, but it's y equals 0. So we're wanting to think it's a whole line. It's the x-axis. So the graph will look, again, eventually what happens is it could get messy in the middle, but eventually the graph goes to 0. Graph goes to 0. Gets close to that x-axis one way or another. Those are our 3 cases. So in your text, I think they may call this the long run behavior. So it's what's happening in the long run when we either go to negative infinity or positive infinity. We either get horizontal asymptotes or we don't, right? The top's bigger, we go off to infinity or negative infinity. If the bottom is bigger, we go to 0, we go to the x-axis. And if they're the same degree, we will go to whatever the ratio of the coefficients are. The other part is the short run behavior. That's where we get the zeros. That's where we get the asymptotes. And I guess we could, let me back up a little bit. These ones where we would get a 0, the potential of getting a 0, is when the numerator becomes 0. So on this one, I think you would see, but if when x was 0, that was crossing the x-axis. The problem here is if you put a 3, it canceled out here, so we actually don't even get a 0 there. We get an undefined because we get 0 over 0. But if we're going to look for where it crosses the x-axis, we would look only at where the numerator is equal to 0. Okay. So we could graph these, find all asymptotes and sketch the graph. So again, your system may ask you to do it. I would say go ahead and graph it with a graphing calculator. That will help you find, again, points and such. We did this one. Again, I first thought, well, I'm going to get I'm going to get asymptotes at x equals -3 and x equals 3. But when I graph it, like, oh wait, at x equals 3, that's going to be a hole, not an asymptote. And so, you know, at -3, I can do this thing. We also know what about horizontal asymptotes for this one? Horizontal asymptotes. We only need to look at x over x squared. What does that reduce down to? 1 over x. So x goes to infinity. What's happening? We're dividing by infinity. This is going to go to 0. So what we know is we get a horizontal asymptote at y equals 0. So there's going to be an asymptote there. So it could look like, I think, what was it looking like? Could go something like this, and I don't think there's a 0. What did the other side look like? Maybe like this. Maybe this one was down here. I think so, because anyway. But again, we could go back, and actually we've already graphed it. So let's keep this. Okay, yeah, it's this one. So part of this is if you graph it, you'll see what it looks like, and then come back and try to graph it, and then you can kind of think, what else did I need to think of? But these asymptotes, where these asymptotes are, you know it's kind of going to go there. Sometimes it's hard to tell. Is it on the bottom, like down here, or should I draw it like this? Well, in this case, the calculator will tell us. It doesn't really show that, but if you wanted to show the horizontal asymptote, you could even draw that in. You put in y equals 0. In this case, let's change the color. Let's make it orange, and let's make it a dashed line. So you can draw them in there. And that, again, Desmos does a nice job of helping you learn these things, but then also use your graphing calculator so you know how it works on your handheld, how it's going to look. But you can definitely use it as you go through for the homework. Okay. So be able to do those kind of problems. And then, so 2.6, not Module 9. And that'll get you through the last part on rational functions. Again, there may be they may bring in some of this long division. You can kind of get at that. You can see where zeros are. But the main thing with rational functions are horizontal and vertical asymptotes. And again, those we looked at those. And the horizontal asymptotes are what's happening way out at the wings, out of negative infinity, positive infinity. The horizontal asymptotes are created by division of 0. So those are there. There could be x-intercepts, and again, that'll occur wherever the numerator equals 0. So those are the types of things we end up looking for, and then that allows us to sketch the graph and go forward. But we're also able to use our calculator, use Desmos or something to actually take a look at the graph first. And sometimes that's a better way to learn, because it's, try to do something with a blindfold, you might be able to do it after you learn how to do it, but you want to probably learn with all your everything you have. Questions? Doing okay? Okay, so this weekend, what's our goal? Try to get as much of the homework finished up as we can. Start working on the review. Get a list of whatever questions you still have. If you can't, if you're struggling, bring those. Send them to me, so then I know what we're doing. Tuesday, open day for questions, review. Look for messages from me as I maybe make some solution videos that will help. If you send me something, hey, can you explain this part a little deeper? I can make a brief video, post it. But next week, Tuesday, we're reviewing. What are we doing on Thursday? Taking the test here, so we'll be all ready for it.